All right. Welcome everyone to the 65th meeting of New Directions. Just a minute, let me check that it's indeed the 65th. Yeah. Welcome everyone to the 65th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Alexey Elagin from Edinburgh, and he will be speaking to us about dimensions for triangulated categories.
Thank you. So what I'm going to talk about is a result of our joint work with Valery Lunts, and I have to admit that this work wasn't completely successful, as you probably will see. So I think that everyone knows here what triangulated categories are and what for they are used. So let me only say that they are very natural in geometry and algebra. We have two main sources of triangulated categories, one coming from geometry. When you have an algebraic variety, you can consider its derived category of coherent sheaves. That's example number one of triangulated category. And when we have something like algebra or a ring, we can consider its derived category of representations. That's example number two coming from algebra. And we can try to call this categorical algebraic geometry when we try to study varieties through studying their derived categories and trying to find on the side analogs, reflections, interpretations of some constructions, theorems, facts that we have for varieties. And in this manner, sometimes it can be reasonable to consider also more general triangulated categories and to think that they are also categories of sheaves on some non-commutative algebraic varieties. These varieties do not exist, but we can assume that they have derived category of coherent sheaves, and this category is just some triangulated category T having some nice properties similar to the properties of categories coming from genuine varieties. So we can say that non-commutative algebraic varieties are reasonable triangulated categories. And before going further, let me say a couple of words what reasonable or good can mean. So a minimal reasonable answer is that we consider triangulated categories coming from algebraic varieties and also all admissible subcategories in such. And another way to say what a good triangulated category is to say that that's a category having the form perfect complexes over some smooth and compact DG algebra. And the reason for the second answer is that all two triangulated categories, all two types of triangulated categories that we like are good in both senses. So derived categories of coherent sheaves on smooth projective varieties are good. For the first notion of good, that is trivial, and for the second, that is a result maybe by Lunts or Keller or other guys. And for derived categories of modules over finite dimensional algebras of finite global dimension, the derived categories of representations are also good.
Hi, Alexey. There is a black rectangle covering part of your title. Is that intentional?
That's what Zoom does. I would like to remove it, of course, but actually I have no ideas how to do this.
Yeah, now it's okay.
Now it's okay because some time has passed, but I'm afraid that any new slide, or maybe no. Okay, is it good now?
Yeah.
Good. So for categories of the second type, they are good in the sense of the second answer, more or less for trivial reasons, and in the sense of the first answer by a result of Orlov about geometric realizations of DG categories. So normally I will think that a good category is the category of the form perfect complexes over some smooth and compact DG algebra for our reasons. And I will refer to this as to good. So what are we going to do, or what one would like to do, is to define dimension of an uncommutative algebraic variety. So as soon as they are called varieties, it's natural to understand what is the dimension of such an uncommutative variety. So it means that we are looking for a reasonable notion of dimension for good triangulated categories. So what one would like to have for this notion? There are some natural properties of good dimension function that one would like to have. So dimension of a category coming from geometry should be equal to the dimension of the original algebraic variety. Dimension should be non-negative, and it should be zero only in trivial cases, whatever it means. We would like dimension to be monotonous, so a smaller object has smaller dimension. We would like dimension to be additive under tensor products. It corresponds to the fact that for varieties, when we take direct product of varieties, the dimension is summed up. And taking direct product of varieties corresponds to taking tensor product of triangulated categories. Or actually, there is no such thing as tensor product for triangulated categories. You require to have a DG enhancement to define this tensor product. But as soon as we are studying good triangulated categories, this is well defined. Also, dimension should be constant in deformations. It should be constant for good families of categories. Dimension should be constant under taking quotients of finite group actions, and there are many other properties that one would like to have. So that's only the first one that come up into one's mind. So I have to say that actually our motivation for our work was a bit different. We did not have such properties when studying notions of dimension that I'm going to talk about. But still, it seems that it is natural to state these properties first, then to discuss two the notions of dimension that we have, and then to see which of these properties are satisfied, which are not. And okay, so let's go on. I would like to tell about two notions of dimension, one called Rouquier dimension, which is well known, and other can be called Serre dimension. This is a relatively new notion. So for a Rouquier dimension, it was defined by Rouquier. Now it's often called just dimension. It can be defined for any triangulated category without any additional assumptions. Roughly speaking, it is the minimal generation time. So what does it mean? Let me recall some definitions. Assume that we have a triangulated category and an object in this category. We can try to generate more objects having this one by taking cones, shifts, and direct sums and direct summons. And we are trying to calculate how many different operations do we need when we get new objects. So everything is for free except for taking cones. We count only cones. So G0 is family of objects that can be generated without taking cones. So they are direct sums of shifts of this generator. At this moment, I don't take direct summons. Then GK is a family of objects that can be generated by taking shifts, direct sums, and at most k cones. So this f is constructed as a cone of a morphism from fk-1 to f0. So one more cone added. Then I denote by g with angular brackets to be the idempotent closure of this. So I add all direct summons of objects in gk. And this g is the union of all gk. So this is the minimal thick triangulated subcategory in T containing generator G. And containing object G. G is called a generator if this category is all T, and it is called a strong generator if already at some finite number of steps one can obtain all objects in T. So, for example, if you have never seen this before, it can be interesting and useful to consider this example. Let's take some Noetherian ring. Let's take free module A as a generator. Then any complex of finitely generated projective modules can be generated at n steps from this free module. To see this, note that up to adding some direct summand, this complex can be made to be a complex of finitely generated and free modules, because any projective module is a direct summand in a free module. And if we assume that ki's are free, then this complex can be obtained by taking n cones from its stupid truncations. So if I denoted the complex starting from k1 and ending at kn by x n minus 1, then this long complex is a cone of a morphism from k0 to this x n minus 1. And taking one more cone, we obtain this k. So by induction, we can see that k belongs to a n. And if we assume that our ring has finite global dimension, then any finitely generated module has a projective resolution of length n. So as an object of the derived category, it is isomorphic to such complex. So any such module belongs to the category generated by free module by time n. As we will see soon, in this case, the category on the right side is actually all derived category of finitely generated modules. But this is a little bit more complicated. So the definition of Rouquier dimension is that it is minimal generation time over all generators of this category. If there exists some generator, and it is infinity if no such strong generator exists. So by definition, that's non-negative integer or infinity. So there are first properties of this dimension that were obtained by Rouquier himself in his original paper. These properties are for derived categories of coherent sheaves on varieties or even schemes. So for a quasi-projective and reduced scheme, we have the dimension of this category is at least dimension of the variety, and it is finite. If in addition the variety is smooth, then dimension is bounded from above by 2 times dimension of x. And it is in addition affine, then dimension of the derived category is equal to the dimension of the variety. And moreover, in all examples when this dimension of the derived category can be computed, for smooth varieties, it is equal to the dimension of the variety itself. So it was conjectured, and now it's called Orlov's conjecture, that this holds for all smooth and quasi-projective varieties. Rouquier dimension of the derived category equals to the dimension of variety. But this conjecture is known only for some special, very special cases of varieties, and in any case when it is known, there are some explicit bounds on this generation time for some reasonable generator, and it's absolutely unclear how one could prove this in general. So this conjecture is known for some varieties like projective spaces, quadrics, some other homogeneous spaces, Delpezzo surfaces. It's known for all curves, for some, but not for all rational surfaces, for some very special elliptic surfaces, which are irrational. And quite recently it was proved for all toric varieties, including singular.
Yosha, you know, there is a version of Rouquier dimension which is called countable Rouquier dimension, I think.
Yes.
Are you going to mention it?
Actually, I wasn't planning, but if you asked, I can say a couple of words. Indeed, there is a modification of this definition when one can replace one single generator by a countable family of generators. And one can call this countable Rouquier dimension. And for this countable Rouquier dimension, it was recently proved that corresponding statement is true. So countable Rouquier dimension indeed is equal to the dimension of the variety.
So in some sense it behaves better, right? Then maybe it's a good notion
Yes,
to consider.
I agree. And actually, using this new notion, one can prove that as soon as you have two smooth projective varieties and the derived category of one is embedded as a full subcategory into the derived category of the other, then the dimensions are comparable. So dimension of the first one is smaller or equal than the dimension of the second one. And indeed, this wasn't clear before. And it was one of the motivations for us to study Serre dimension. But it turned out that Serre dimension does not help to prove this. Okay, so now let's return to this discussion. Now let's consider triangulated categories coming from algebra, derived categories of modules over some ring. There is a natural upper bound for Rouquier dimension by the global dimension of the ring, which is this argument that I demonstrated here, but with some modification so that it works not only for modules, but for all complexes of modules. The statement is the same, that free module generates all the category at time equal to the global dimension of the ring. Also, if you have a finite dimensional algebra, then one can say that Rouquier dimension is bounded from above by Rouquier length of this ring. For example, if this is path algebra of some quiver with relations, then it is bounded by the length of the quiver, which is an upper bound for the Rouquier length of this ring. It can be interesting to note that if A has finite representation type, then Rouquier dimension is at most 1. But in general, even if we restrict ourselves to finite dimensional algebras, no one knows what Rouquier dimension of the corresponding category is. It is computed in some examples, but there is no answer and no understanding how does it behave for general finite dimensional algebras.
And what
Okay.
about the countable Rouquier dimension here about this last question?
That's a good question, and I don't have an answer. Maybe that's a good direction to look into. At least there is no candidate for the answer. There is a natural candidate in the case of derived categories of coherent sheaves, but for such categories it is not clear what the answer could be. So now let's turn to third dimension. Actually, it's based on the notion of categorical entropy, or it's parallel to the notion of categorical entropy that was suggested by Dimitrov, Haydn, Katsarkov, and Kontsevich in a very nice paper about dynamical systems and categories. So this can be defined only for categories that are linear over some field and that have a Serre functor. And roughly speaking, this dimension measures how iterations of the Serre functor applied to some fixed object behave in the sense of their cohomology, whatever it means. So there are two ingredients in this definition: dynamics of iterations of some functor, which can be arbitrarily exact and the functor of our category, and the notion of Serre functor. So in principle, one can define dimension with respect to any outer equivalence, but Serre functor is good because it is like an invariant of the category. It is not an additional structure, but it is defined in terms of the category itself. So by the definition, if our category is home-finite over some field K, then a Serre functor is an autoequivalence such that homes from X to Y are isomorphic to the dual space to homes from Y to S of X. This star stands for the dual vector space, and this isomorphism should be natural in X and Y. If such functor exists, it is unique up to an isomorphism, so it's an invariant of the category in some sense, and it can be used for defining other invariants like third dimension. And I would like to note that for triangulated categories that we call good, Serre functor exists. Now, how to produce an invariant from an autoequivalence of the category? At first, let us assume that our category is a category of some complexes. So objects of this category T have cohomology. And let's assume we have an exact and a functor. Let's take some generator, and let's apply iterations of this functor to this generator. We have some complexes. Any complex has support. That's number of positions where this complex has non-zero cohomology, and this support somehow changes when n increases. So let's look how quickly it moves, this support of this complex. To make this definition for any fixed iteration n, let's consider cohomology of this object. Let's take the minimal cohomology. This is some number depending on n, and let's see how quickly it changes when we increase n. So usually this is a negative number, so we take minus sign, divide this by n, and take the limit. That's what's called upper third dimension of category with respect to a functor S. And if one takes the maximal number with non-zero cohomology, we obtain lower third dimension. By the definition, upper Serre dimension is greater than lower Serre dimension. And if our category is not a category of complexes, but just some triangulated category, instead of studying these cohomology groups, one can study home groups from some fixed generator to this changing object. So we assume that there is a generator in the category, and instead of cohomology, we consider shifted home groups from G to iterations of the functor applied to G. And the rest of the formula is the same. So we obtain upper Serre dimension and lower Serre dimension. At least we have formulas. A priori, it is not clear that these limits exist, but it follows from, essentially it follows from the paper by Dimitrov, Haydn, Katsarkov, and Kontsevich that these limits exist. So they are some finite numbers. In principle, they are real numbers, and we can't say anything more at this moment. And it follows that the limits that we have here do not depend on the choice of generator. So they are indeed invariants only of the category. And also from this, it follows that for triangulated categories that we like, that come from geometry and from algebra, Serre dimension is well defined. But for the algebraic case, we would like to assume that the algebra has finite global dimension. It is not necessary, but this is sufficient for the Serre functor to exist. So what can we say about Serre dimension of these two types of triangulated categories? For derived categories of coherent sheaves, it can be explicitly computed because we know that Serre functor on such derived category is just tensoring into canonical line bundle and cohomological shift by the dimension of X. So iterating this, we get tensoring into powers of this canonical line bundle that does not change position of our complex, and cohomological shift gives us motion to the left with speed equal to the dimension of X. So upper and Serre dimensions are equal to the dimension of X. And this is what explains that this is indeed dimension and not some other strange invariant. So for categories coming from geometry, everything is good and well understood. Now let's have a look at the algebraic categories. So we have a finite dimensional algebra having finite global dimension. Then Serre functor on such derived category is given by derived tensor product into bimodule A star. So this is just a dual vector space to A, which has a structure of A bimodule, and tensoring into this bimodule gives a Serre functor on the derived category. So iterations of such functor are tensoring into iterated derived tensor product of this bimodule, and studying dynamics of iterations of Serre functor is the same as studying these iterated derived tensor products of Serre bimodule with itself. Here I have some comments on how Serre functor behaves when we apply it to some modules. So Serre functor sends indecomposable projective modules into indecomposable injective modules. And if algebra A is hereditary, and we take a non-projective indecomposable module, then Serre functor sends it to translation of this module shifted by 1. And now I would like to say that for the case of derived categories of representations of algebras, these formulas have that form. So we take derived tensor powers of Serre bimodule and look at their cohomology. From this formula, we can obtain first natural bounds. We can see that this complex is concentrated in degrees from 0 to minus global dimension of A times n. So dividing this back to n, we get that upper Serre dimension is bounded by the global dimension of this algebra. And once again, this is almost all that we can say in general. If we take some finite dimensional algebras, we normally do not understand what is its Serre dimension and how to compute it. That's a mystery. So what I would like to do then, I would like to show you some examples of derived categories of modules over finite dimensional algebras where we can compute all dimensions. And these examples provide us with some like motivations or with some answers to the questions about properties of these dimensions. So we would like to understand whether Rouquier and Serre dimension can serve as a dimension function, as we discussed in the beginning. And these examples tell us what we can have and what we do not have. So welcome to the zoo. I would like to denote by Q some quiver, by I some ideal of relations in the path algebra of this quiver, by A corresponding finite dimensional path algebra, and by T its bounded derived category. So the first example is, of course, derived category of representations of hereditary algebra. So we have some quiver without cycles. We assume it is connected, and then we have two essentially different situations when this quiver is a Dynkin quiver and when it is not. So if Q is a Dynkin quiver, then the corresponding derived category is fractionally Calabi-Yau. It means that some power of Serre functor is some power of shift functor. To be more explicit, let h be the Coxeter number, then Serre functor 2 power h is the shift by h minus 2. And from this, we can see that dynamics of this functor is the same as dynamics of shift functor. So we can have that Serre dimensions, both are equal, and are equal to the ratio of h minus 2 and h. Also for Rouquier dimension, it equals to 0, and I should have said that Rouquier dimension is 0. It's equivalent to the saying that our category has only finitely many indecomposable objects up to a shift. And for the right category of modules over hereditary algebra, any indecomposable object is a shift of an indecomposable module, and there are only finitely many indecomposable modules for Dynkin quivers. So this is the case, and Rouquier dimension is 0. Now, if quiver is not Dynkin, then there are infinitely many indecomposable modules, so Rouquier dimension is 1. And the same holds for Serre dimension. To see this, one can return back here and see that taking some indecomposable module, which is non-preprojective, we can apply many times Serre functor to this module, and anytime we get a shift by 1. So Serre dimension should be equal to 1. So, as you can see, Serre dimension can be a rational number and not an integral number. For k A2, where A2 is a quiver with two vertices. Serre dimension is 1/3. That's the minimal possible positive, the minimal known positive value of Serre dimension. For Ka3 we have 1/2 and so on. Now, example number 2, we consider path algebra. Is it a question? So for the quiver AN, we can impose relations that any composition of arrows is 0. It turns out that such derived category of modules is equivalent to the derived category of modules over path algebra in the same quiver, but without relations. So this category is equivalent to the category considered in previous example, and we have the same values for Rouquier and Serre dimension. But compared to this example, global dimension of our algebra is now big. It's n-1. So the bound of Serre dimension by the global dimension is not sharp at all, as we can see here. Also, it can be interesting to note here that we can take any set of quadratic relations for paths in this quiver. Not all squares of arrows are equal to 0, but only some compositions of two consecutive arrows can be made equal to 0, and still this derived category would be equivalent to the derived category of paths in AN without relations and have the same dimensions. Now let's have a look here, the ring of dual numbers. Here we have algebra which is has infinite global dimension, but still corresponding derived category has Serre functor, because bimodule A star here is isomorphic to A. In particular, it has finite projective dimension. So Serre functor for this category T is just identity functor, and it means that Serre dimension is 0, while global dimension is infinity and Rouquier dimension is 1. In this case, we have, of course, we have only 2 indecomposable modules over this algebra, but we have infinitely many indecomposable complexes, which are not modules. Also note that this category T, as well as the category of perfect complexes over A, are not good in our sense. Now, more interesting example, Auslander algebra of the ring of dual numbers. It's given by a quiver that you can see here, and one relation y and then x is 0. For such algebra, one can compute that now Serre dimensions lower and upper are different. Lower Serre dimension is 0 and upper is 2. It comes from the computations saying that Serre functor sends indecomposable projective P0 to itself and indecomposable projective P1 to a complex of length 2, where we have P1, P0, and P0. So applying this once again, we get a complex of length 4, etc. So left end of this complex does not move, and lower Serre dimension is 0, while the left hand side of this complex moves with speed 2, and upper Serre dimension is 2, as well as the global dimension of this algebra. This is something very unlike what we have for derived categories of coherent sheaves, where complexes do not tend to spread. That's a modification of the previous example. One more cyclic quiver with some relations. So y times z and z times x are 0, while x times y is not 0. This algebra still has finite global dimension equal to 3. And it happens the same for Serre dimension. Lower Serre dimension is 0, while upper Serre dimension is the maximal possible, it is 3. And I would like to note that Serre dimension, lower Serre dimension equal to 0 can only happen for path algebras of quivers with cycles. If the quiver has no cycles, then lower Serre dimension must be positive. That's an example of the same thing that I have just told when upper and lower Serre dimensions are different, but both are positive. Actually, here I have two examples at the same time. One example of the algebra where lower and upper Serre dimensions are different and positive, and also this is an example of a family of algebras and a family of categories. So you can see the quiver, and I put relation saying that composition of x and y is lambda times z, where lambda is some scalar. So changing this lambda, we get a family of algebras and a family of categories. And of course, we have two essentially different fibers of this family. Lambda is 0 and lambda is not 0. If lambda is not 0, then this relation simply says that z is the composition, so it is not needed. We can remove that, and we get a path algebra of quiver A3, for which we know everything from example 1. But as soon as lambda is 0, we get a different algebra, an anisomorphic, and it can be computed that now upper Serre dimension is 2, as well as Rouquier dimension is now 1. So we cannot hope that these dimensions are constant in families. They are not. But we see that Rouquier dimension and upper Serre dimension, they like jump in one special point. So there is a hope that they are like semi-continuous. Okay, we had some expectations about behavior of tensor products, so let me demonstrate an example of dimensions for tensor products of algebras. We can consider different tensor products of path algebras of quivers AN. Any such tensor product has lower Serre dimension equal to the upper Serre dimension, because any such tensor product is fractional Calabi-Yau. So we can compute its dimensions, its Serre dimension. That would be the sum of Serre dimensions of the factors. And there are exactly 3 such products of path algebras of quivers AN that have Serre dimension equal to 1. This is A2 to power 3, or A3 to power 2, or product of A2 and A5. These 3 algebras are very nice. They appear in many contexts, in many situations. For example, corresponding derived categories are equivalent to derived categories of covariant sheaves on weighted projective lines of tame types, or to derived categories of equivariant covariant sheaves on elliptic curves with a non-trivial finite group action. So from this point of view, it's natural that their Serre dimension indeed is 1. So because these are curves which have dimension 1. Is a little bit bigger. Can you hear me?
Yes?
Yes.
Yeah, my computer says to me that internet connection is unstable, so I am asking. Okay, there is just one more, or two more examples. This is an example that does not come from finite dimensional algebras, but from finite dimensional DG algebras. So now let us consider just two vertices and some graded vector space of arrows between them. Let us consider corresponding path algebra as a graded algebra and as a DG algebra with zero differential. This algebra is smooth and compact, so corresponding category of perfect complexes is good. And for this category, we can compute Serre dimension just by computing iterated tensor powers of Serre bimodule. And the result is very surprising. It says that this Serre bimodules spreads in both directions, so that it's one end goes to the right and other end goes to the left, as soon as this vector space is indeed a graded vector space. So there are different gradings in this vector space. Let me denote by W the graded width of this vector space. So it's difference between the maximal and minimal numbers of non-zero components in this vector space. Then Serre dimensions are 1 plus W and 1 minus W. So in particular, if W is at least 2, then lower Serre dimension can be negative. And this example is really important, and there are many categories having this form, because as soon as you have a triangulated category with a DG enhancement, which is generated by two exceptional objects, by exceptional pair, then this category is isomorphic to this, where vector space V is nothing else than graded X group of X's from E1 to E2. And let me demonstrate a special case of this category, which is interesting because it can be realized as a subcategory in the derived category of coherent sheaves on a Hirzebruch surface. So let's take Hirzebruch surface F3. This is a projectivization of a vector bundle O plus O of 3 on P1. So it has structure of a P1 fibration over P1. Let F be any fiber, and let negative section of this fibration be S. This is a curve with self-intersection -3. Surface X is smooth rational of Picard rank 2, and we can consider the following exceptional collection of line bundles that we have on the left. We can take OX and mutate it to the right through OX of S. The corresponding complex I denote by E. This is again an exceptional collection, and now let me remove OX of S and leave only OX of minus F and E. These two exceptional objects form an exceptional pair. Let me consider category generated by this exceptional pair, and let me know that there are home groups between these two exceptional objects in 3 degrees, -1, 0, and 1. So this category T has the form studied there with W equal to 2. So Serre dimension is -1 lower Serre dimension and +3 upper Serre dimension. That's it. I call this bad exceptional pair because here we have that Serre dimension, upper Serre dimension of a subcategory is bigger than Serre dimension of the original category of coherent sheaves on this X, which has third dimension 2, because this is a surface. Now, let me summarize what we have. I recall that we had some list of ideal properties that a good notion of dimension should have. Now let's see what we indeed have for Rouquier dimension and for Serre dimension. Actually, as you can see, neither of them can serve as a good dimension function, because some properties fail for some dimensions. So for dimension of the derived category of coherent sheaves, Serre dimension is good, but for Rouquier dimension we do not know actually whether this is always so. That's called Orlov's conjecture, and even if this is so, this is a very complicated question. At least dimension of the category is at least dimension of the variety. So for categories of 0 dimension, we can prove it for Rouquier dimension that a category with Rouquier dimension 0 must be derived category of representations of a linking quiver. So we had this example in the beginning, and surprisingly, this is essentially the only possible example of a triangulated category with Rouquier dimension 0. For third dimension, we have seen that it can be negative, at least for lower third dimension, and there are reasonable examples of algebras providing lower third dimension equal to 0. For upper third dimension, we hope that still it should be positive, and non-negative, and we expect that it is 0 only in trivial cases like semi-simple categories. But this is only a conjecture. We do not know how to prove this, even in the case of derived categories of modules over finite-dimensional algebras. Now, monotonicity. Rouquier dimension is monotonous, more or less, by the definition, because if you have an admissible subcategory, then you can project a generator of a category onto the subcategory, and this would be a generator with the same generation time. And for third dimension, we have seen that it is non-monotonous. This example says that lower third dimension is not monotonous. For category studied here, lower third dimension is 0, and if we take subcategory generated by first two projective modules, then it's equivalent to the categories of representations of quiver A2, which has lower third dimension 1/3, which is positive and greater than this 0. And our last example, number 9, demonstrates that that upper third dimension also is not monotonous. It's 3 for subcategory generated by two exceptional objects, while third dimension of derived category of coherent sheaves on F3 has third dimension 2. For tensor products, it can be easily demonstrated that third dimension is additive, while for Rouquier dimension it is not additive, as we can see looking here. We take algebras like KA3 of paths in quiver A3. Its derived category has Rouquier dimension 0, but we take tensor product and we get Rouquier dimension 1. So it is not additive. But in all examples that we have, dimension of the tensor product is greater than the sum of dimensions, so probably it is like sub-additive. Probably always one has inequality here. And finally, dimension in families. As we can see from this example, Rouquier dimension can jump at some special points, and upper set dimension also can jump. Unfortunately, I don't have a ready example where lower set dimension can jump down. But what we know and what we have proved is that lower set dimension is lower semi-continuous, so it can only jump down at special points, and upper set dimension is upper semi-continuous, so it can jump up in special points. And it would be very interesting to understand whether Rouquier dimension is also upper semi-continuous. We do not know whether it is so. So let me summarize that we don't currently have any good notion of dimension in the sense of these original properties. We don't know if such function exists, and if there are probably many such functions, very many such functions. But what we can say that Rouquier dimension and Serre dimension are not very good in the sense of these properties. And also there are very many open questions and open problems that one could work on. So let me list some of the questions that I consider interesting. One is about behavior of Rouquier dimension in families. Whether one can prove that it is upper semi-continuous. Then Serre dimension, which is by definition only a real number. It would be interesting to understand whether it is indeed always rational. That would be nice to have this, right? Also, it would be nice to prove that Serre dimension for good categories is positive, upper Serre dimension. There is a weaker version of monotonicity for Serre dimension. As we see, Serre dimension lower and upper are not monotonous, but now let us assume that they are equal, as we have for derived categories of covariant sheaves or for fractionally Calabi-Yau categories. Assume they are equal. Is it true under this additional assumption that Serre dimension is monotonous? That's a question. And finally, it's natural to try to compare these two dimensions. They are defined from very different points of view, so probably they reflect different properties of the category. But once again, in all examples that we have, Rouquier dimension is bounded from above by upper Serre dimension. So probably this is always so, or at least probably if two Serre dimensions are equal, maybe under this assumption, Rouquier dimension is bounded from above by Serre dimension. This is also not known. So in general, I think that studying Serre dimension and Rouquier dimension for the categories of finite dimensional algebras is an interesting problem, because there are many questions and there are a few answers. So I would like to have more examples. Where these dimensions are known. And another interesting idea is to look more into these properties and maybe to add some other properties that would allow one to deduce from these axioms some properties of this function, and probably to prove that such function exists or that it does not exist, or maybe to compute this function for some examples using only axioms and having no definitions. this is also an open direction. So it seems that I have finished and my time is over, so I would like to thank you and to ask if you have any questions.
Thank you, Alexey. Can we all unmute ourselves and give the speaker a round of applause, please? Okay, if you have any questions for the speaker, you can ask them now.
Yes, I do have a few questions. Do you hear me?
Yes.
Okay, I was not sure if the microphone works in this PC. So I wondered, how does the Rouquier dimension or the Serre dimension compare to generators of, say, hearts of T structures or something like this, or to T structures in general? Are T structures useful in this context somehow?
How are they related to T structures?
I know you didn't mention T structures at all, but that's just something that I thought could be related somehow.
I only can say that there are some other notions of like dimension that are using not T structures but stability conditions. So for stability conditions you have like phase of objects, right? And you can view how applying some functor like Serre functor or some other functor, how it acts on phases of objects and extract some invariance from compatibility between end functor and stability conditions.
Okay. Thanks. Very big question.
Thank you, Lucas. Any other questions?
If I may ask another one.
Sure.
Yes.
I think you said it and I probably missed it, but can you repeat how do the Rouquier dimension generators, so those minimal generators typically look, for example, for Dynkin quivers? I think you mentioned it, but I missed it somehow.
I did not say it.
Okay.
For Dynkin quivers, which give us category of Rouquier dimension 0, you simply need to take all indecomposable modules. There are finitely many of such, and take their direct sum. This is the generator, and any object can be obtained from this generator just by taking direct sums of shifts of direct summons.
Okay.
And if you like, for example, to prove that Rouquier dimension is 1 while global dimension is 1, you just take free module, and that's the generator.
Okay. Thanks.
Any other questions for Alexey? What was the triangulated category you said is the only known example of a triangulated category with Rouquier dimension 0? Can you go back to?
So what's the question?
Towards the end of your talk, didn't you mention a triangulated category that you said is the only possible candidate for or the only known example of a triangulated category with Rouquier dimension 0?
So the only example is derived category of modules over Dynkin quivers.
Yeah. Okay. Yeah, I was just I
or well,
remember.
you can take you can take direct product of several such, of course, but as soon as the category is connected, surprisingly, that's the only example.
Yeah, thank you. Okay.
Maybe I have a question. So
yeah, please go ahead, John.
for the geometric examples, the dimensions seem to be fairly closely related to the dimension of the variety. But for the algebraic ones, they seem to be very different from global dimension. Do you have some kind of explanation for why? So somehow these things basically don't seem to relate to global dimension at all.
Well, global dimension is not an invariant of a triangulated category. So you can have derived equivalences between derived categories of modules over different algebras that have very different global dimension, right? So as soon as I look at the triangulated category, I do not know the global dimension. So it cannot be a candidate for something that is related with Rouquier dimension or some other dimension.
Okay, so suppose I take a bounded derived category of a finite dimensional algebra with certain global dimension. If I'm looking at other faithful hearts in that, does their global dimension have to be lower than the global dimension of the heart of which is the bounded derived category that you start with?
Well, you can start from one and arrive at the other. Or you can go in the opposite direction, right? Start from the other and arrive at the first. So they can have different global dimension.
So
it means that no one can be bounded from above by the other because they can be opposite.
And they can
you might ask
examples where they're different.
Yes, actually, let me return to my presentation. So here it is. This is path algebra of quiver A2 with all possible relations, so any composition of arrows is 0. And this algebra is derived equivalent to the same quiver, but without relations. So here global dimension is n-1, it's big. And if we have no relations, then it is 1.
Okay, thank you.
You could ask what happens if we take the minimal global dimension over all hearts or something like this.
I guess overall faithful hearts. So
maybe faithful, yeah. Maybe faithful hearts.
Otherwise, it's almost always 0. Right?
Yeah. That would be more reasonable, and actually, that can be an interesting invariant. But I'm afraid I cannot say more about it.
Okay, thank you.
Thank you, John. Any other questions for Alexey? So there is something in the chat.
Yeah, I just thought, I think there's a paper by Keller and Krause about global dimension of hearts of T structures coming from tilting objects. I think that's related to a previous question, or did I misunderstand this?
Sounds like it might be related.
Yeah.
Thanks for telling this. I would like to have a look at this paper.
So this has an explicit upper bound. I don't remember it exactly, but I think it's something like global dimension of the heart you start with, the standard heart, plus 2 times the width of the tilting object.
2 times
the cohomological width of the tilting object. But I'm not quite. There might be a ±1 or something like this somewhere.
Sounds interesting.
Thank you. I'll have a look too.
Yeah. Any other questions? If not, let's thank Alexey again. Okay, thank you all for coming.
Thank you.
Yeah, thank you very much for the talk.